All right, welcome to the Explainer. Today, we're breaking down a really cool topic. We're going to trace the path of a signal all the way from the physical world right into the very heart of an electronic circuit.
Yeah, have you ever really thought about that? It all boils down to a pretty simple idea. You take some kind of information, you turn it into electricity, and then you make it way, way more powerful. But how does that actually work? Okay, let's dive in.
Okay, so first things first. Before we can do anything with information, like electronically, we've got to capture it. We need a way to grab it from the world around us and translate it into an electrical signal.
And that super critical first step, that's the job of something called a transducer. You can think of it like a translator, or a bridge, really, between our physical world and the world of electronics. A microphone turning your voice, those sound waves, into a voltage? That's a transducer. A camera sensor turning light into an electrical current? Yep, that's a transducer, too.
So, okay, we've got our signal, now what? Well, now we need to be able to talk about where it came from, but, in the language of circuits. And engineers, well, they've come up with a couple of really clever ways to model it.
So here they are, the two main ways engineers think about a signal source. On one side, you've got the Thevenin model. It basically pretends the source is a perfect voltage source, kind of like a perfect battery, with a little bit of resistance right after it in a series. Then on the other side, you've got the Norton model. It sees the same source as a perfect current source, with that resistance sitting next to it in parallel. And here's the cool part. They're totally equivalent. It's just two different ways of looking at the exact same reality. This is awesome for engineers because they can just pick whichever model makes the math easier for the circuit they're working on.
So our signal exists, but honestly, it's usually super, super weak. It's just a tiny little whisper. To be useful for anything, it needs a hero. It needs something to come in and give it a massive boost.
And that process, of course, is called amplification. And let me tell you, this is one of the absolute cornerstones of all microelectronics. Without it, forget about it. Your phone wouldn't be able to pick up a cell signal, your headphones, totally silent. It's that important.
But wait a second. You can't just create energy out of thin air, right? The laws of physics say no. So where does all this extra power come from? How does an amplifier actually make a signal stronger? Well, it's not magic, but it is some seriously clever engineering. Here's the trick. The amplifier is hooked up to a bigger power source, like a battery or the plug in your wall. It takes that raw DC power and uses it to build a brand new, much stronger output signal. The key is that the tiny little input signal acts like a stencil or a template. It's not providing the power itself, it's just controlling how the big power from the DC supply is shaped. So you get a magnified, perfect replica of the original. Okay, before we peek under the hood of an amplifier, there's something really important we need to cover. Signals basically come in two main flavors, analog and digital. So analog signals, think of a smooth ramp. They're continuous, they can be any value within a range. Digital signals, on the other hand, are like a staircase. They can only be at specific levels or steps, usually just a high or a low, which we call a 1 or a 0. What's really cool is that a ton of modern gadgets actually use both. It's called mixed signal design, and it lets them get the best of both worlds. Now, the actual guts of an amplifier can be mind-bogglingly complex. But the good news is we don't need to get into all that to understand what they do. We can use a simple black box model. We just need to know about 3 key things to get a handle on how it behaves. All right, first parameter, input resistance. Let's use an analogy. Imagine you want to measure the air pressure in your car tire, but your gauge lets out a ton of air every time you use it. That's a terrible gauge, right? It's changing what it's trying to measure. A good amplifier is like a perfect pressure gauge. It should have a really, really high input resistance, so it can look at the input signal's voltage without sucking a bunch of current from it and messing it up.
Second, we have voltage gain. This is the whole reason we're here, right? This is the amplifier's job description. It's just a number that tells you how many times bigger the output voltage is going to be compared to the input. So, a gain of 100? Simple. The output is 100 times the input voltage.
And finally, number 3 is output resistance. Think of this as a little bit of internal resistance, like a hurdle the newly amplified signal has to jump over on its way out the door. Now, if you want to deliver that powerful new signal to the next thing in the circuit, say a speaker, you want that hurdle to be as small as possible. A low output resistance means a signal gets out easily and efficiently. And this simple 3-part model is awesome because it helps us understand some really clever circuits. For example, check out something called a buffer amplifier. Here's the weird thing. Its voltage gain is 1. 1. It doesn't amplify the voltage at all. So you might be asking, what's the point of it then? Well, its job is to be a perfect go-between. It has that super high input resistance we talked about, so it doesn't mess with the original signal, and it has a super low output resistance, so it can powerfully drive whatever comes next. It's like an electrical diplomat, basically, connecting two parts of a circuit that wouldn't normally get along.
Okay, so we have our model, but there's a twist, a big one. It turns out an amplifier doesn't treat every signal the same. Its performance can change, like a lot, depending on the signal's frequency.
So is the gain just a single constant number? Nope, not at all. The truth is, every amplifier has a sweet spot, a specific range of frequencies where it performs at its best. It's kind of like how your stereo has big woofers for the low bass frequencies and tiny tweeters for the high frequencies. Same idea.
And that effective range, that sweet spot, in engineering, we call that its bandwidth. And this behavior is usually created on purpose using some really simple circuits called filters. Their whole job is to let certain frequencies pass through while blocking others.
At the most basic level, you've got two kinds of filters. A low-pass filter, which, you guessed it, lets the low frequencies, the bass, pass through. And a high-pass filter, which lets the high frequencies, the treble, pass through. Most amplifiers are really a clever combination of these, which is how they carve out that specific bandwidth where they work best. So, how do you know where the bandwidth, begins and ends? How do engineers define that edge? They look for something called the half-power point. It's the exact frequency where the signal's power has dropped by half of its peak. That's the cutoff. And in engineer speak, that half-power point has a special name, the 3 decibel point, or the 3 dB point. That's the magic number that marks the edge of the bandwidth.
Now, what happens outside the bandwidth? The amplifier doesn't just, shut off. Its performance starts to drop, but it does so at a very steady, predictable rate. And to visualize this whole thing, how the amp behaves at low frequencies, in the middle, and at high frequencies, engineers use a special kind of chart called a Bode plot. It's basically the amplifier's performance blueprint.
Okay, let's do a quick recap of this whole journey. It starts in the real world. A transducer turns it into a tiny electrical signal. That weak signal gets a huge power-up from an amplifier, which is grabbing energy from a DC source. We can understand that whole process using a simple model with just 3 parts: input resistance, gain, and output resistance. And finally, we learn that the whole thing is super dependent on frequency, which defines the amplifier's bandwidth.
So think about this. That whole journey we just followed, for one single signal going through one single amplifier, that's the fundamental building block. It's the basic operation that happens billions, even trillions of times a second inside every microchip, every computer, every single smartphone on the planet. What you've just learned isn't just a random piece of electronics. It's the very first step to understanding pretty much all of modern technology.